Hi, I'm Janet Shiver of Central Washington University, and today we're going to be finding maximum and minimum values for quadratics. Why would we care to do this? Well, finding maximum and minimum values we call in mathematics optimization. And a lot of times in, say, business, you want to maximize your profits or minimize your costs. Maybe you're building a garden and you want to maximize the area. Or perhaps you're making a product and you want to minimize the amount of material you have to use for it. These are the types of problems that we're going to be looking at today and learning to solve. To do that, you're going to have to use what we've learned in the past two lessons. First thing is how to write the quadratic functions, or how to write the functions, even those that aren't quadratic. We'll see how to solve those today as well. And then, of course, the second thing is, how did we find that maximum and minimum value? Where was that located on our parabola? Well, of course, you probably remember it being located at the vertex. So we're either going to have to complete the square to find that vertex, or we can use that nice little formula we discovered a few lessons ago to solve it. So let's go ahead and start by looking at some examples. All right, we're going to go back to one that we did just the other day, very similar to it. Farmer Brown would like to fence a rectangular field for his cows to graze in. If he has exactly 1,024 feet of fencing, what should the dimensions of the rectangular plot be in order to maximize the area for the cows to graze in? What is that maximum area? All right, we're going to start these problems exactly like you did the problems in our previous lesson. We need to start by writing those equations. So again, we're going to draw and label a picture. So rectangular field, we've got our length and our width. Write the equation representing what it is that you are looking for. All right, we are looking to maximize area. So we know that area is equal to length times width again. Write the second equation from the information given in the problem. Well, once again, we have a certain amount of fencing, and as we know, fencing goes around the outside of the field, so we're talking perimeter again. And we know the perimeter of a rectangle is 2 lengths plus 2 widths. I know the perimeter, it's 1,024. And then I need to solve for a variable. Now you'll notice in a lot of these problems, they aren't going to bother to give you which variable to solve for, so it's up to you. I'm going to, since we did it last time, I'll solve for L again. I'm going to divide everybody by 2. Well, let me subtract my 2W first. And then divide everyone by 2. Giving me 512 is equal to, minus W equals L. All right, fourth step we know is to combine the two equations. So I'm going to substitute what L is equal to into my area formula. And then, of course, I'm going to distribute the W. All right, so far nothing new. It's the same thing that we did the other day. Here's where the new part comes in. Now we're going to take this equation that we've written, and we are going to, in this case, find the maximum, find the area where the area is at a maximum. To do that, if you'll remember, in a parabola in which W squared is negative, my parabola is going to be concave down, and so the point right here would be my maximum. And of course that point is located at the vertex. Now, for these problems, most of the time, that's all you're looking for. So in this case, probably the better strategy is to use that nice little vertex formula we found rather than going through the whole process of completing the square. So that's what I'm going to use. All right, my variable in my equation is W, so I'm going to be solving for W. And if you remember the formula, it was negative B over 2A. Negative B, well, here's my B, 512. over 2 times A, and A is -1. All right, dividing 512 by 2, we get 256. All right, so the width that will maximize the area is going to be 256 feet. Okay, now here's where I always make my big mistake. I've done all this work, I've gone through, I've gotten an answer, I'm thrilled to death, and I move on. Step 6, fully answer the question. Okay, I have made this mistake many a time, not completing what they've asked for, just getting one part of it and then moving on. What is it that they really wanted me to find? Well, they want the dimensions, both dimensions, not just width. So I need to first of all go back and find the length as well. You can plug in many different places to find length. Probably the most convenient is in this equation you found in number 3. So I'm just going to plug back in. Length is equal to 512 minus my width, which is 256. And surprise, surprise, the length ends up being the exact same thing. So it looks like the rectangle that's going to maximize the area happens to be the square. Okay? So I've got my length and my width now. Did I finish answering the question? Always check. What are the dimensions? Got them. What is the area? Okay, I haven't found the maximum area yet. And again, I've got different places I could do this. I could plug back into my area formula right here, calculate it from there, or I could just use what I know about a rectangle, and length times width is going to give me area, so I'm going to do it that route. Area is equal to 256 times 256, or 256 squared. So my area is equal to, that comes out to be 65,536 feet squared. All right, that one was a relatively simple one. Let's look at one that might be a little bit more challenging. All right, the following figure shows a square inscribed within a unit square. Okay, first of all, let's make sure we all know what unit square means. Unit square means has a length of 1. Now, it didn't tell us 1 what? 1 foot, 1 inch, 1 centimeter, but we know that the length of this outside square has a unit of 1 something. All right, for which value of x is the area of the inner square a minimum? This time we're going to minimize something. And what is that minimum area? All right, so let's start, as we always do, by writing an equation to represent what we're looking for. We want to minimize the area of this inside square. Well, knowing that it's a square, and I know this side is x, this side must also be x, so my area for my square is going to be x times x, or just x squared. Now here's the tricky part. We need a second equation that we can get from the information given. Now occasionally you're going to get something like this where it's not so obvious. It's not just, hey, here's the perimeter, or hey, here's the volume. It's a little bit more challenging. I need to somehow relate this inner square to this outer square. All right, and what I'm going to suggest we do is, down here you'll notice that somewhere along these sides, the square is going to be hitting at different points. It's going to divide each side of my unit square into 2 parts. Okay, I'm just going to call this part over here T. This length from my point to the corner of the square is going to be T. Well, if that's the case, and this side is 1, then this part right here has to be 1 minus however long this was, T. Okay, may still not be apparent what other equation we can get out of this. I'm going to write these two on this side as well. That would mean this side is t, and this is 1 minus t. Now take a look and see if you can figure out a way to relate x to the t's that I've written. I think most of you probably noticed right here, you have a right triangle. Okay. And what do I know about right triangles? Well, again, back to the Pythagorean theorem, I know that one leg squared plus the other leg squared will give me the hypotenuse squared, and that will pull in this unit square in relation to the inner square. So look for the Pythagorean theorem in many places in these equations. All right, so let's see if we can write our second equation then. So t squared plus 1 minus t squared is equal to x squared. And believe it or not, I'm going to be a little lazy here. I'm going to leave it solved for x squared, and that's just because I look up here and see what my other equation was in terms of, and I notice, hey, it's equal to x squared, so why change it? So I'm not going to actually solve it for x this time. All right, but I will go ahead and expand this side, t squared plus, don't forget when you are squaring a binomial, be sure that you use the distributive property on it and not just say 1 squared plus t squared. All right, so we get 1 minus 2t plus t squared equals x squared. Add your t squareds together, 2t squared minus 2t plus 1 equals x squared. All right, and there's your second equation. Step 4, you know, is to combine the two. And the reason I left this again as x squared is because this was already in terms of x squared. So we're going to substitute in area equals x squared. So my area is equal to 2t squared minus 2t plus 1. And I have this wonderful quadratic function now that I can certainly find the vertex for. All right, notice that again in front of my t squared, the 2 is positive. So I know that this parabola is concave up. Therefore, that vertex right there is going to give me a minimum because it'll be the lowest point on that parabola. All right, so we're going to find the vertex by using our formula again. This time our variable is t. So t is equal to negative b over 2a. So negative b will be 2 over 2 times a, which is 2. So that's 2 over 4, or 1/2. And no units were given, so it's 1/2 unit. Okay? All right. Again, though, my biggest mistake as a student and sometimes as a teacher as well is to forget to answer the question. So let's go back and see what it asked for. For which value of x is the area of the inner square a minimum? We know now that t is 1/2. Did that give me what x was? Now I got t. So how in the world am I going to find out x? Well, I need to make a substitution. Over here I see that x squared is equal to 2t squared minus 2t plus 1. So let's make sure that we answer the question. So x squared is equal to 2 times 1/2 squared, I'm just substituting in, minus 2 times 1/2 plus 1. X squared is equal to 2 times 1/4 minus 1 plus 1. X squared is equal to 1/2